Our last watery talk today will be Dr. David Jones, BGS colleague of mine, who has also done a lot of work during the CUSP programme on estuarine and marine contamination. So Dave, over to you.
Thank you, Bree. After that very interesting diversion, I'm afraid I'm going to have to drag you back to geochemistry and more geological matters. I'm going to give you a kind of overview of some of the work we've done in the Clyde estuary. It will just be very much a slight flavour of the work we've done, which involves quite a lot of work and quite a lot of different colleagues within BGS. As a bit of initial background as to why we've done the work, I mean, estuaries are important habitats we've just seen for fish and shellfish, and also for things like birds and mammals, but they're subject to human impacts, both from urban centres, from impacts from up the estuary, and from impacts from the seaward side, as well as from urban centres like Glasgow, which actually sit on the estuary. And they act as sinks for sediments from both marine and fluvial sources. And those contaminants themselves within the sediment have the potential to cause harm to the biota. They have the potential to be stored within the sediments for lengthy periods of time and then re-released back out to impact biota in the future over the long term. There have actually been relatively few detailed geochemical studies of estuaries anywhere, and certainly that's true of the UK. And a lot of the drivers for our work are legislative drivers. Treaties like OSPAR, which is a treaty of the North Atlantic area, which we have signed up to, which has a very challenging aim, actually, of trying to get concentrations in the marine environment back down towards zero for man-made substances and back down to background levels for naturally occurring substances, which seems to me to be an extremely difficult thing to try and achieve. And we're also driven by European legislation. And one of the things which sparked off BGS's interest in estuaries was this quote at the bottom from the editor of the Marine Pollution Bulletin back in 97, saying that this would be a really appropriate sort of thing to do. And we actually started off our work in the Mersey estuary originally, and then moved on from there because of the interest, in particular of Glasgow City Council, to the Clyde as our next target estuary. And since then we've done a certain amount of work in the Thames estuary. What we've done, rather than just collect samples and analyse the chemistry of the samples, we've tried to put them in some sort of geological context. So the initial part of our investigations has involved a lot of geophysical work with a variety of techniques like shallow seismic with boomer, side-scan sonar to map features on the seabed surface, and the use of multi-beam bathymetry to give us very detailed maps of the bottom. And this basically shows how through the years of our work we've extended out from the work we initially did for the City Council within the urban and inner estuary area into the middle estuary, which was, so the early work was from about 2002 to 2003. In 2004 we moved out into the middle part of the estuary and did some survey work with the hovercraft you see here towing a surface-towed boomer system for seismic data. And then we moved further out into the outer estuary. And then we had a further opportunity to gather some data further to the west. So we're moving out more into the sort of open marine realm of the outer part of the Firth of Clyde and out of the estuary proper, and gathering data within this outer area here and extending over into the Holy Loch area to look at different kinds of contamination there from different types of sources. And particularly as well to include in this sort of area here a couple of dredge spoil disposal sites which we thought it would be interesting to look at. So just to give you an example of some of this geophysical data, this is a multi-beam bathymetry plot of that latest work from 2007, with the deep water in blue and the shallow water in red. And you can see immediately there a lot of features, some of which are natural features and some of which are man-made features, and some quite unusual things, some very strange sort of little groupings of three imprints within the sediment over in this area, which were quite intriguing, for example. And we've done an interpretation of that, or colleagues have done an interpretation of that, and we're really seeing a mixture of glacial and post-glacial natural features, some of these ridges, these glacial moraine features, and some of these deep features, perfectly natural, things like a landslip over here. But we're also seeing human-induced features, most notably this area of dredge spoil disposal here, and these strange triangular marks which we've interpreted as being perhaps jack-up rig marks actually going into the bottom. They're so regular and so, each repeat is almost identical to the other, that they have to be man-made, I think. So we've used all that really to put our observations of the more near-surface sediments in some sort of overall context, and to give us some sort of feeling for what the Quaternary and post-Quaternary history of the area has been, and then where our contamination study fits in within that. We've also been able to map out the surface sediment types, because the contamination is very much, the amount of contamination is very much driven by the sediment type. In general, the finer the sediment, the more contaminated it will be. So what we see as a general kind of oversimplification is muddy sediments within the inner part of the estuary, a middle part of the estuary which is dominantly sandy, and then an outer part of the estuary which returns to mud. And as we go to the west, that mud persists and becomes most notable in this deep water area in Loch Long. And we can see as well a different type of sediment on the surface in this dredge spoil disposal area. So turning now from the sort of background context to the actual geochemical work, what we've done is a whole range of sampling of both the surface sediments and of shallow cores that we've taken of the sediments down to maybe 2 or 3 meters, using a whole range of techniques, some of which are shown here, some from vessels and some simply by hand sampling on the exposed intertidal flats. And what we've done is then subjected those sediment samples to a whole suite of analysis to look at a whole range of inorganic contaminants and a lot of organic material as well in addition as background data on things like particle size analysis, geotechnical properties, and the mineralogy and petrology of the sediments to try and put everything in context. And all that has been pulled together into a project GIS, with the aim of trying ultimately to distinguish what the background levels of elements are within the estuary and what contaminants are on top of those background levels, and how that appears in terms of the contamination history of the estuary and the total amount of contaminants present, and then saying something perhaps in a general way about the sources of some of those contaminants. So to show you a few examples, some here from Solveig Lass Evans, who's got a poster outside with some of the inorganic work where she's looked at the whole suite of samples together. And the example I've picked here is lead, but I could have shown several others. And what we've got in the top plot is just the straight raw concentration data. And you can see there are a number of higher points within both the inner estuary and the outer estuary. What we've done in the plot below is to normalize the sample data to aluminium as a proxy for grain size effects, to try and remove the effect of the different grain size on the geochemistry. And that actually doesn't have that marked a change on the overall distribution. It does have some change in detail. The other approach we've taken is to, as with some of the onshore samples, is to look at sediment guideline levels and how the values of our elements compare to those guidelines. Now, there are a whole range of guidelines, and it seems to me no one set of guidelines is actually perfect. A lot of them have flaws in terms of some of the guideline values being far too low, being well within the range of natural background variability. But what we've taken here, or what Solvay has taken, is the Canadian freshwater sediment guideline values, and you can see a number of samples on the top plot for arsenic, copper and zinc, which exceed the sediment quality guidelines. You can see that a much larger range of samples for chromium exceed the guideline values, and we've heard earlier about the processing of chrome in the city of Glasgow. But I think actually a lot of this is in fact natural high chromium levels rather than necessarily contaminant values. And we see also other high values within the inner and outer parts of our area for nickel and lead at the bottom. The other thing that we've tried to do is look at the natural background levels within our locality, within our sampling area, rather than using these guidelines which have been developed elsewhere, to actually look at what are the baseline values within the estuary. And one of the approaches for doing this is to look at the value in cores, where you'd expect that as the sediment gets older, you're going to eventually go to sort of pre-industrial levels of elements. And this is what we see in this core here as an example. It's a muddy core which doesn't look particularly on the face of it to change a great deal with depth. But we've got this very marked change from the top 40 centimeters or so in all of the elements plotted here, chromium, lead and arsenic, down to near constant values. So what we've done is taken those values in the lower part of the core, in the uncontaminated part of the core, as an expression of the baseline, the natural background value. And then we've looked at how our values for the surface sediments compare to those averages for the background. And I've plotted on here, just out of interest, where the sediment quality guideline values fall for those elements. And you can see for chrome in particular, the natural background is actually quite high, is actually quite close to the sediment guideline value. And in fact, if you take CFAS's dredge spoil disposal guideline values, it's 2.5 times the lower limit action level that they set. So it is showing that the natural chrome level is quite high in this area. So if we do that process, we can then look at samples which exceed the background value by a certain number. So in this case, what Solvay has done is look at samples which are 5 times, have an enrichment factor of 5 times the natural background. And that then brings us down to a relatively small number of samples, a couple within the sort of shipyard and dock areas of inner Glasgow, and then a bunch of samples which are high in a series of elements in the former submarine base in the Holy Loch. Looking now at organic contaminants briefly, we've looked at one of the groups of elements we've looked at are PAHs. And with PAHs, you can look at the ratio of the different isomers, and that tells you something about the source of the contamination, with there being a distinction between pyrolytic PAHs, which are produced by combustion products. So in Glasgow, probably mainly from coal burning in the earlier industrial history of the city, and you'll see that they're predominant in the inner Clyde area, where virtually all of the PAHs are of that pyrolytic type. As we go further down the estuary, we get more of a mixture of burning products and petroleum products, this petrogenic group, which is going to be mostly things like oil and diesel spill kind of contamination. The other thing we found was very interesting was looking at the distribution of elements down some of the cores. We've got a number of man-made contaminants, like PCBs, which were only introduced in a relatively recent time frame. So they first appeared in about 1940. They reached a peak in production and use in the 1970s, and then they declined after they were banned completely in the 1980s. And what we seem to have down the cores is quite a nice reflection of that historical use of this contaminant group in particular. And we can see the same thing for a number of other contaminant groups, which I'll come on to. So we can actually see within different cores, there's 4 data for organic elements plotted here for 4 different cores. And we see that the position of that peak varies within the cores, but we in general seem to have the same kind of general profile, which follows the historical use and then discontinuation of those kind of contaminants. And if we look at, rather than the PCBs, we look at the PAHs, which are reflecting burning, we've got a much longer history than going back to really the start of industrialization within the city. So that's giving us a much longer time frame than the PCBs. If we look at things like cesium-137, again, this is a man-made radionuclide which is produced from atomic weapons and nuclear fuel for power station production. So it comes from atmospheric weapons testing in the 60s, which was at its peak. It comes from Sellafield discharges, which were at their peak in the late 1970s. And then it comes from events like Chernobyl. So we can see major peaks here, which probably relate to the Sellafield discharge. In other cores, we can see double peaks, which perhaps reflect the Chernobyl element as well as the earlier Sellafield peak. And all of these different contaminants are telling us quite a consistent story. And perhaps what is most impressive is the lead isotope chronology, where if we compare the red line here, which is one of our data down one of our cores, with a historical record of airborne airborne lead uptake by Scottish moss produced by John Farmer back in 2002. And I could have added a whole load of other data which are in this paper, but to avoid a very messy and confusing diagram, which you're welcome to look at in the paper, I've kept it simple. And I think you can see that the trends in the atmospheric deposition of lead are very well matched by the core. So we can have real confidence that we are seeing a chronological history of contamination in the estuary. And what we're picking up is the early days of mining, where it's basically a geological lead signature. We then move later into a petrol lead signature, where most of the lead would have come from Broken Hill in Australia and have a distinctive signature. And then in the decline that we see at the top of the cores is probably a reflection of the stoppage of use of lead in petrol and the move to unleaded fuels. So in conclusion, we can see that the contamination within the estuary reflects the industrialization of the area and nicely reflects the historical evolution of that industrialization. We can broadly define the contamination sources within the area, but we're not able really to pinpoint sort of individual sources at the moment. We see that lead isotopes match very well to establish detailed chronologies, and our other anthropogenic and natural element contaminants also fit well into that history. But this is only part of the story, and we've heard from others, and Mark Cave has a poster on this as well, that really the form and the bioavailability of these contaminants is equally important, if not more important, than the actual global concentrations that we have. I didn't show it, but we've also looked at some what we might call emerging contaminants, some newer materials like PDBs, which are flame retardants, and they're present within the estuary as well at relatively high levels, but they're not covered by any kind of guidelines at the present. I'd like to finish by acknowledging the support of organisations like the Glasgow City Council, SEPA, and the Glasgow Humane Society. All provided financial and logistical support for our work. The crew of the various vessels who helped us to collect the samples, and a whole raft of BGS and other colleagues who I've hopefully managed to name here, and to thank you for listening.
Many thanks to you, Dave. It's a lovely summary of a large body of work, and it's really interesting to hear it pulled together. We're pushed for time. I think we've got time for one question, if anybody has a question.
Scope for matching your seabed mapping of sediments to some of the habitat mapping that you're referring to previous at all. Have you considered doing that?
We've considered it. It's not something we've got around to doing it, but it would be interesting to combine it, certainly.